Yeah, so we were talking about vector functions and we looked at a few graphs. We got an idea of how we can get a sketch of them, how we can analyze separately, say, the x and the y coordinates to see that it goes on a circle and then see what happens with the z coordinate. We saw some examples about a few of them that were interesting. And today we're gonna be started talking about calculus. If you haven't done so, write your name on the chat area. I see some of you are doing that already. Remember, that's how I know you were present here for class or not. Okay, so we're gonna go to the book so to show how we can talk about limits and continuity first, and that is going to be actually quite straightforward. We won't be justifying things with a lot of detail. Specifically, this is what we have here. So we say that a vector valued function has a limit of L. So one vector approaches another vector. So we write it like so, right? We write like this limit, the limit of the vector function r of t when t approaches a is L. If the magnitude of the difference vector, so if the vector that it measures the difference between those two vectors, so if you subtract one vector from the other, that magnitude goes to 0. If that happens, we say that the limit of the vector function r is L. Now, that's the straightforward definition, but in reality, the way you're gonna use it is what is written right here in the bottom part. So right here in the bottom part, what it says is that if you can do the limit, see, this is, let me put a square around it. This is the important one that you want to know how to do. So if, excuse me, if you want to do the limit of a vector valued function, you can do it by doing the limit of each one of the components, assuming each one of the components has a limit, which will be the case for most functions we have in this class. So that's the easiest way of doing a limit. And once you learn this way of doing it, then the problem of doing limits is just like doing, instead of doing one problem, it's like you're doing 3, right? Because you're doing the limit on the x component, you're doing the limit on the y component, and you're doing the limit on the z component. And that's how you do it. So to do the limit of a more complicated function, that's how you do it. And the only thing you need to remember is if one of these 3 fails, so if one of these 3 does not exist, then the big one, the limit for the vector function doesn't exist. Okay, as easy as that. In the same way, we can also talk about continuity. So for continuity, it's right here at the bottom. We say that a function is continuous if you can do the limit by simply plugging it. So here is the definition, right here at the bottom, right here. So some function, f, g, h, with components f, g, and h is continuous at a point A, at a time A, provided that when you do the limit, you get r of A. If you can do the limit by plugging the number, we say it's continuous at time A, at t equals A. Okay, so let's do an example on next page. And we looked at the graph of this one yesterday. Let me remind you. It looked like this, right? It looked like I like to think of it as a piece of a cable that is winding over itself, right? Something like this. And so that's the function is cosine pi t sine pi t e to the negative t, and the domain is the positive values of t. So here are a few limits. that we want to do. Let's go to the right. So part A asks to evaluate the limit when t approaches 2. Let's go to the page. Remember that since I cannot really write bold, what I usually do is I show it to you with an arrow on top. So we need to evaluate this limit. And it's as easy as this. Well, what is this r of t? According to our definition, this r of t has these components: cosine pi t, sine pi t, and e to the negative t. So all you need to do is do the limit of each one of the pieces. So the answer will be the limit cosine pi t, comma, the limit of sine pi t. That's what I was telling you. It's kind of like doing 3 limits, right? Instead of doing 1 limit at a time, it's like this type of problems give you 3 limits. But if they're all done the same way. So these 3 are continuous functions. We know sine is continuous, cosine is continuous, the exponential function is continuous. That's from last semester, 158. So all we need to do is plug the number 2, right? So in this case, this is cosine 2 pi t, sine 2 pi t, and e to the negative 2. And you can simplify it if 2 pi, like there's no t, my bad. T equals 2. And cosine of 2 pi we know is 1, sine is 0. So that's the answer, 1, 0, e to the negative 2. So that's part A. Now part B says about the limit when it goes to infinity. And for this one, you can see that this one, e to the, when t goes to infinity, e to the negative t goes to 0. So the last coordinate will go to 0. But these other 2 don't have a limit because sine and cosine, when you go to infinity, they still goes up and down, right? Up and down from 0 to, from between -1 and 1. So if you write y equals cosine of pi t, that function looks like this. And when you go to infinity, it doesn't have a limit, right? It oscillates between -1 and 1. So what's the answer to this one? Does not exist. Does not exist because the limit of cosine pi t when t goes to infinity does not exist. As long as one of them doesn't exist, then the answer to the big one will not exist as well. Okay? So the limit when it goes to infinity, it does not exist. And we knew that when we looked at the picture because it keeps winding, right? So it's like this thing comes around and comes around and comes around and keeps turning and turning and turning. And it gets closer and closer to 0. So every time it goes lower, lower and lower, but it never reaches 0. It appears so in our graph because at some point the thickness of the graph is more than the distance to 0. So that's it for that part. And then for part C, it says, at what points is R continuous? And this is an easy question to answer as well, because look at over here. Where is cosine continuous? Everywhere. Where is sine continuous? Everywhere. Where is e to the something continuous? Everywhere. The 3 of them are continuous everywhere, therefore the vector function is continuous everywhere. So the answer is for every real number, because sine pi t, cosine pi t, I don't know why I flipped the order, and e to the negative t are all continuous on all real numbers. Good. Questions? Good. So we'll move on now to, so that's finishes 14.1. We just left a little bit of that for today. And we'll continue now with the next section of the book, which is in 14.2. And to begin with, we'll start talking now about the derivative, right? What is the derivative of a vector function? And for that, I'm going to show you what is the idea, and you will see something, again, it will turn out to be something that we're familiar with, and that's the good thing. So what is the general idea for the derivative? And here it is. You have it right there. The general idea is to look at this definition. So we have, if we want to know what is the derivative at time t, what we look for is for a little increment in time, delta t. And so we add a little bit delta t to t, and we see what kind of vector we have. And then we subtract the vector r of t. So we do the difference of the two vectors. And then we divide by that delta t. It looks exactly like our definition, if you remember, but with the difference that we're not using h, right? Your definition for the derivative, it used to be f of x plus h minus f of x over h. But this should remind you of that, right? That's exactly the same. And this is the interpretation. So let me show you the drawing that follows. The drawing that follows explains what is it that we're doing. So you have a vector, let me look at this one first. So you have the vector r of t, and the vector r of t, this one over here that I'm gonna draw, this one, right? And then you're considering the vector r of t plus delta t. So a little bit of time passes. Where is the vector now? And if the graph was like this one, where it's moving towards the right, you know, like going like that, then after a little bit of time, you would be here. That's r of t plus delta t. Then what's the difference? And the difference vector, the second one that I drew minus the first one, it's this one over here, this red one. Yes? So that's that difference vector. So we want to know what is that difference vector when we divide it by delta t. Delta t is a constant, right? When we divide it by the constant, the scalar delta t. So, or we multiply it by 1 over delta t. And then what explains that is this one over here, the picture on the right. So, oops. For the picture on the right, you see what is it that we're doing. So these blue vectors are getting closer and closer to r of t. And when that happens, these red vectors, this red vector that we drew is not going to be a secant vector anymore. It's going to be closer and closer to the tangent vector, right? So this r prime of t is going to actually have that interpretation. R prime of t is always going to point in the direction of where the object is moving and tangent to the curve. So r prime, the vector, the derivative, we call it the tangent vector. Is the tangent vector at the point P, right? If the limit exists. So if the derivative exists, the answer, r prime of t, will be the tangent vector at the point P. Okay. Now, how to calculate it? That's the next thing, right? So perfect. We get it, Professor, and we get the interpretation, and we sort of see how this red vector is going to look like this red tangent vector. But how do we calculate the derivative? And fortunately, the answer to that is easy. So let's go to the page over here, right? So if you want to evaluate the derivative, if you want to find out what is this limit, the only thing you need to do is break it down into its components, right? So how do you do the difference of these two vectors? Well, you do the difference of the x component, the difference of the y components, and the difference of the z components. And that's exactly what follows on the next line over here. So let's take a look at it. So so it's a little bit long, so we need to zoom out a little bit. So this one over here is when we plug t plus delta t, right? Look, we have f of t plus delta t. That's the x component. And remember, you can write vectors with the commas. So the bracket, comma, comma, and then the other bracket. Or you could use I, J, and K. It's up to you, and it's the same thing. So here, the book uses I, J, and K. So the I is the x component, the J is the y component, and the K is the z component. So this red one is corresponds to this one. And then the next one that I'm going to draw, it corresponds to the green one, the R of t. And that's this one over here. All right, and all of that is divided by delta t. Good. So the next thing you want to do is combine the ones that go together. So over here, you combine the ones that have i's. So f of t plus delta t and f of t over here, both of them have i's. So in other words, you put these together. Let me make it thinner. And over here as well, right? So these two terms, f of t and f of t plus delta t, go here. Then these two, the g and the g, go here. And last, this h and this h over here go there. All right? And then what happens when, so now look at those that we have right there. What are they? It looks like f, the function f on delta plus delta t minus f divided by delta t. G plus delta t minus g divided by delta t, and h plus delta t minus h divided by delta t. Okay? So what is that? Well, this is exactly the definition of f prime, g prime, and h prime. So those are the derivatives of the components. This is the derivative of the x component. That's the derivative of the y component. And the last one is the derivative of the z component. So in other words, see, the way to do the derivative is the easiest thing in the world. All you need to do is do the derivative of each part, right? The derivative of the x part, the derivative of the y component, and the derivative of the z component. That's how you figure out the tangent vector. So let's look at the definition on the next page, and then we'll start doing a few examples. So here's the next page. And right here is the relevant box. So as you can tell, it says, if you have a function that with components f, g, and h for the x, y, and z components, and f, g, and h are differentiable on an interval, then the vector function r will be differentiable, and the derivative of the vector function will be the derivative of f, comma, the derivative of y, of g, comma, the derivative of h, right? So in other words, just take the derivatives of the corresponding components, provided the derivative is not zero. If the derivative is not zero, then that represents the tangent vector at the point corresponding to r of t. So that's how you can get the vector that is tangent to the curve, assuming it's not zero. If it is zero, remember, it's not really a vector, right? It has no magnitude. It's just, then we cannot say it's tangent because it doesn't have any magnitude. Okay, so let's do this example one that you see over there. It says compute the derivatives of the following vector functions. The first one is t cubed, comma 3t squared, comma t cubed over 6. And then we have another one there. So let's go to the page. Okay, so how do we do it? I mean, and remember, you can write it like this, or you can write it as follows: t cubed I plus 3t squared j plus t cubed over 6k. Either way, okay? So let's do the derivative. What is the derivative? Super easy. You do the derivative of t cubed. Bam. The derivative of 3t squared. There you go. And the derivative of t cubed over 6. So that would be t squared over 2. And you can write it like this, or you can write it with the I, the j, and the k. Up to you. Either way is correct. Whatever you prefer. Okay? Easy peasy, right? Let's do the part B. So for part B, we have e to the negative t I plus 10 root t j plus 2 times cosine of 3t k. And just like I was telling you, I mean, there's nothing new here. It's just like we need to do 3 problems instead of 1, right? So here's the derivative. The derivative of e to the negative t, that's negative e to the negative t. The derivative of 10 root t, that will be 5 over root t. Here, chain rule, right? The derivative of cosine is negative sine, so this will be minus of 3t times the derivative of 3t, which is 3 times k. So that's actually 2 times 3 is negative 6, right? And that's it. Okay, easy peasy, as I was telling you. Now, oftentimes you want to, let's go back to the book, you want to look at a normalized tangent vector. So the tangent vector, the thing is that it's tangent, but sometimes it's bigger than others. So it in a sense measures how fast you're drawing the curve. If the vector is too big, it means you're going fast. If the vector is smaller, it means you're slowing down or you're going slower. And then sometimes you would like to have it so that it's always the same length, and or to get an idea of only the direction. And for that, we have this definition. It's called the unit tangent vector. And it's precisely like it says right there in the book. It says in situations where we only care about the direction, but not the length of the tangent vector, then it's relevant to think about making it unit. And the way we make it unit, we already learned that from our excursion with vectors. The way we do it is by dividing by its magnitude, right? So right over here, the way we do it is right here. This blue box tells you what is it that you're supposed to do. You take the r prime vector and you divide by its magnitude. So let's take a look at some examples. This will be example 2. It says find the unit vectors, the unit tangent vectors. And it's denoted capital T, as you can see there, right there on the screen right now. Good. So let's figure it out. So here's part A. The vector is r of t equals t squared 4t for ln t, for t greater than 0. That's the domain. Okay. So here's our definition. The vector t, the unit tangent vector, is supposed to be r prime divided by the magnitude of r prime. correct? So let's figure out R prime. So this, let's leave this pending. It's our formula. So let's figure out R prime first. And so what's the derivative of t squared? It's 2t. The derivative of 4t, that's 4. And the derivative of 4 ln t, and that's 4 over t. Right? That's step number 1. So we already have this ingredient for our formula. Step number 2, get the magnitude. How do we get the magnitude of a vector? It's the square of each of the components, add them up, and then take the square root. So it's 2t squared plus 4 squared plus 4 over t squared. And this becomes 4t squared plus 16 plus 16 over t squared. Right? Okay, great. So we're now ready to write down the answer. So what's the answer going to be? Here it is. So we want the unit tangent vector. So it's this number, this is the first component divided by this, comma, next component divided by this. Now in the book, they simplify this a little bit. You could do that. If you were to do something else with this vector, then of course it would make sense to simplify it. But if this is the final end answer to this question, then why, right? Let's just leave it like this. This is the correct answer. That's all we really care about. Right? And that's it. That's the tangent unit vector. Okay, let's do part B. So for part B, the problem is R of t is 10, 3 cosine t, 3 sine t, between 0 and 2 pi.
Professor?
Yes.
I just had a question.
Go ahead.
When writing the answer, could we also write it as r prime of t multiplied by the scalar of the magnitude? So we don't have to write it each individual term? Or do we have to apply to each term?
You can do it the way you're suggesting. So for those of you, so Michael is saying, if I could have written the answer like this, so could I have written the answer like this? 1 over 4t squared plus 16 over t squared times the vector 2t 4 over t. Will we leave it like this? And the answer is yes, right? I just wanted to put it over here so that you realize it's really one vector, right? But yes, you could leave it like this. So this is okay. Okay. Good. So let's continue. So what is r prime here? This would be the derivative of 10, that's 0. The derivative of 3 cosine t, that's negative 3 sine t. And the derivative of 3 sine t, that's 3 cosine t. What is the magnitude of this vector? 0 squared, negative 3 sine t squared, and 3 cosine t squared, which is 9 sine squared plus cosine squared, which in this case we should obviously simplify, right? It's considerably easier. This is 1, and the square root of 9 is 3. So that magnitude is 3 all the time. So in this case, it actually makes sense to write the t of t. So you can write it as Michael had suggested, which is just 1/3 of this vector. Or if you want, you can multiply the 1/3 by, and then it's just 0 negative sine t cosine t. Either way is correct. Okay? Very good. Let's move it along. So what else? So let's go to the book. And the next important topic to talk about here is the different types of rules we have for derivatives, and they're going to be really I'm trying to do here. They are going to be what you expect. So let me just go to the next page. So specifically, if we have a constant vector function, the derivative of it will be, well, 0, right? So because it's going to be the derivative of the first component, which is going to be 0, the second component, which will be 0, and the third component, which will be 0 as well. So this is what I'm talking about here, starting with the one on the top. The derivative of a constant vector is 0. It's like a constant function. If you have two vector functions u and v, and both of them have derivatives, then the derivative of the sum is the sum of the derivatives. Whoop-de-doo, right? Not surprised. Now we have the product rule. Now careful here, because it depends what product we're talking about. For number 3, the product we have is a scalar. This f of t is a scalar. It's like a number times a vector. So if you want to do the derivative of a scalar times a vector, you can do the derivative of the scalar times the vector plus the scalar times the derivative vector. And that's the product rule. So it looks exactly like a regular product rule, but be careful because these are two different types of objects, right? One of them is a number, the f, and the other is a vector, the u or the u prime. We also have the chain rule. If you have u evaluated on a function, but this function again is a scalar. If that happens, your chain rule works. So it's the derivative of the vector u evaluated in f times the derivative of the scalar f. And 5 and 6 are interesting too. They are also like the product rule, but they are the product rule for our other products that we learn about, right? Remember that we learn about the dot product, and we also learn about the cross product. Well, these two over here show you that for those products, the product rule applies as well. So on the first one, it says that the derivative of the dot product of two vectors, you can do it by doing the derivative of the first dot product the second plus the first dot product the derivative of the second. Kind of like the product rule, but with dot product. And then on the one after that, we have the derivative of the cross product. Remember, the cross product is a vector, right? And it works the same way. You can do the derivative of the first cross product the second plus the first cross product the derivative of the second. It works the exact same way. Okay, so let's put it in practice. We'll do example 3, which has a bunch of these for us to figure them out. Okay, let's switch to the page. Okay, example 3, we have compute the following derivatives. So u of t is t times I plus t squared j minus t cubed k. And v is sine ti plus 2 cosine tj plus cosine tk. And here are our questions. First, what is the derivative of v of t squared? Let's start with that one. So, I mean, of course, you can do this two ways. You can just plug t squared in v and then take the derivative. That would be one way, an acceptable way. And the other is to use kind of like the chain rule, which is the second way. Okay, so I'll show you both ways. So, two solutions. First solution, and I call this straight substitution. This is probably the one you would think of doing first. So what is it that I mean by this? I mean plug t squared in here. So if you plug t squared, what do you get? You get sine of t squared, then 2 times cosine of t squared, and then cosine of t squared. So plug it first, and now do the derivative. What's the derivative? The derivative of sine of t squared. Well, that's cosine of t squared times, by the chain rule, the derivative of t squared, which is 2t. 2 cosine of t squared, that would be, the derivative of cosine is negative, so it will be negative 2 sine of t squared times the derivative of t squared, which is 2t. And last, it will be the derivative of cosine, which is negative sine of t squared times 2t, right? And that's it. That's the first solution. Second solution is like using chain rule. Using the chain rule we just learned. So in that case, the derivative would be v prime evaluated in t squared times 2t, right? And what is b prime? Well, b prime is the derivative of sine. Now you can see it right here. The derivative of sine, that's cosine, but evaluated in t squared. The derivative of 2 cosine, that's negative 2 sine evaluated in t squared. And last is the derivative of cosine, that's negative sine evaluated in t squared. And all of that times 2t. It's like scalar multiplication, right? And look at them, how they are the same. See, over here is just like you already multiplied the 2t over each one of them. But it's the same answer. So which one is better? Well, it's up to you, right? What do you want to do? You want to do the chain rule individually to each one of these 3 pieces, right? You're going to need to do that chain rule 3 times. Here, here, and here. Or would you rather do it only once? But then you later have to multiply by each one of the components if you wanted to, because you can leave it like this, right? There's nothing wrong with leaving your answer like this. So it's up to you. There is no better way. Both of them work correctly, and they both more or less require the same amount of effort. All right, let's take a look at part B. So for part B, we want to do t squared, the derivative of t squared times v of t. Again, this one you can do 2 ways. You can multiply t squared times your vector over here. So multiply t squared times this one, times that one, and times that one, and then take the derivative of each piece. So you're going to need to do the product rule 3 times. Or you can do it the new way. And I'm going to do it the new way, right? I'd rather follow the new way. I mean, you can always do the straightforward way. But we're learning a new thing, so let's do it with the new way. With the new way is the product rule. So the product rule would be the derivative of t squared times v plus t squared times b prime, right? And then the derivative of t squared is 2t, that's easy. V, I just copy, so it's sine t, 2 cosine t, And the derivative of v is also easy, is the derivative of sine, which is cosine, the derivative of 2 cosine, which is negative 2 sine, and the derivative of cosine, which is negative sine. And that's it. You could leave it like that if you wanted to, or not. If you don't want to leave it like this, then you need to multiply these two, and then multiply these two and add them, and so on, right? So it will be 2t sine t plus t squared cosine t, comma, 4t cosine t minus 2t squared sine t, comma, 2t cosine t minus t squared sine t, right? So this last step is not needed, by the way. It's okay to stop right here. So, questions so far? See, in general, the new way is better. I think in this one it's better because instead of having to do the product rule 3 times, here we don't really do the product rule. We just leave it like that, right? So we do the product rule in the more at a higher level, so to speak, right? We do the product rule on a higher level, and that amounts to less work because you don't need to do it 3 times in the low level. In the low level, you need to do it 3 times. In the higher level, only once. Good. Next one, part C. Now, what about doing the derivative of the vector u dot the vector v? Okay. And again, there's 2 ways of doing this one. You can first do the dot product of u and v, and then do the derivative, and that's gonna amount to applying the product rule many times, because when you multiply u and v, here you have them right here. When you do the dot product of u and v, you're gonna have this times that, and the k with the k, and then you're gonna have to apply the product rule 3 times there. Whereas over here, it will only require to do the product rule once, okay? So by the new product rule we learned, this will be u prime dot v plus u dot v prime. So that's it. Well, we only need to know u prime. And you can't see u. So u was, let me write it here, small. So here's what u was. U was t squared negative t cubed. So u prime is going to be 1, the derivative of t squared, 2t, the derivative of negative t cubed, negative 3t squared, dot v, and v is sine 2 cosine cosine, plus u, which is t squared negative t cubed, times b prime, and b prime is cosine negative 2 sine negative cosine. And you could leave it like that, right? Or you could do the dot product. See, if you do the dot product, is this dot product, that one, that's sine t plus 4t cosine t minus 3t squared cosine t plus, and then t times cosine t, t squared with negative 2 sine t, and negative t cubed with negative cosine t becomes positive t cubed cosine t. All right, and that's the answer to that one. If you want, then you can later factor the sines and the cosines. Depends on what do you need this expression for later on. All right. Okay, what's next? Next is higher order derivatives. What if can we do the second derivative or the third derivative? Yes and yes. We can keep doing multiple derivatives, and the way we do it is the way you would expect. So the second derivative, it means take the derivative of the derivative, and so on. So let's go back to the book. So to do higher order derivatives, you just do the derivative of the derivative and so on. So let's do this example 4. So for example 4, it says compute the first, the second, the third, etc., all the way to the first, the second, and the third of the function r of t equals t squared 8 ln t 3e to the negative 2t. So there's no shortcuts here. To do the second or the third derivative, you first need to do the first derivative, all right? So here we go, r prime. What is r prime? The derivative of t squared, that's 2t. The derivative of 8 ln t, that's 8 over t. The derivative of 3e to the negative 2t. The negative 2 comes down, so it will be negative 6e to the negative 2t. And I'm going to write this as 8t to the negative 1 for the purposes of doing the derivative again, right? Okay. Second derivative, the derivative of 2t, 2. The derivative of 8t to the negative 1, it will be negative 8t to the negative 2. The derivative of negative 6e to the negative 2t, it will be negative 6 times the derivative of this, which is e to the something, times the derivative of the top, which is negative 2. So it will be 12, because the negative 2 multiplies the negative 6, e to the negative 2t. Good? As a second derivative. Third derivative. The derivative of 2, 0. The derivative of this one, negative 2 comes down, it's 16t to the negative 3. And here the negative 2 comes down, so it's negative 24e to the negative 2t. And so on, right? We could keep going. We could do the third derivative, the fourth derivative, the fifth, and so on, if needed. Okay? All right. Like I said, this is not difficult at all. It's like the stuff we're doing already, but many times. So you need to do it for the first component, the second, and the third. Let's take a look at the next topic, which is now integration, right? Well, not surprisingly, for integration, it again works the same way. So to talk about an integral, what we're going to be doing is looking at the antiderivative of the first component, an antiderivative of the second, and an antiderivative of the third. So if you have that, you can find the indefinite integral of a vector function as the vector that has the 3 antiderivatives, plus a constant, right? A constant vector. So this constant vector is made up of 3 different constants, the constant 1, constant 2, and constant 3. All right? So in other words, you just do it by doing it in each one of the components. So you integrate the first component, the second component, and the third component. That's exactly how it's done. And you may also do definite integrals the same way, all right? So definite integrals will be done the same way. But first, let's do, I'll show you an example here first in the book. So you see, it's not even worth it really this one is really so easy. Then we'll do another one on the paper. So here's example 5. So say that you want to integrate this function, the t over t squared plus 2, the square root of that I, plus e to the negative 3tj, plus sine 4t plus 1k. How do you do it? Well, you integrate each one of the pieces. So the first one over here, by doing a u substitution of the bottom, you realize that the integral is the square root of t squared plus 2. E to the negative 3, the integral is e to the negative 3 times negative 1/3. And sine 4t plus 1 is negative 1/4 cosine 4t plus t. And each one of them has their constant, right? Constant 1, constant 2, constant 3. So you can write it like this without the constants, and then plus a big constant c vector. which consists of C1, C2, and C3, for the I, the J, and the K, or the X component, Y component, and C components. All right, let's do another one here. So let's do example 6 right here on the page. So it says find R of t such that, so this time we're going to have an initial condition. I'll show you in a moment. Well, in fact, that's right here in the bottom. So let's put it so that R prime of t is 10 sine t, and R of 0 is j. Let's check it out. All right, so how do we do this one? Well, we're given the derivative. So to find the original function, we need to find the antiderivative. So in other words, the indefinite interval. So this RT that we're looking for, it will be the indefinite interval of R prime. So in other words, the indefinite interval of this, 10 sine t, right? Now, how do we do this? We integrate each one of the individual components. So what is the integral of 10? That's 10t plus a constant, but I'm going to put the constants at the very end, all right? Then the integral of sine will be negative cosine, and then the integral of t will be t squared over 2, and then plus a constant vector, right? Or you can do it like this, or you can do plus c1 plus c2 plus c3. I'd rather use one thing, so to me this looks better. Okay, so that's the answer of the general antiderivative. But we already know there's tons of antiderivatives. There's too many. For every constant, you get a different one. So this time we can pinpoint the one we want using this initial condition. So we have an extra piece of information. It says R of 0 is j. So let's use that piece of information. R of 0 is j. J, by the way, is 0, 1, 0. Yes? And what is R of 0 if we plug it in here? Well, it would be 0 minus cosine of 0 plus comma 0 squared over 2 plus c. So this is 0, negative 1, 0 plus c. So then you can solve for c. So what is c going to be? The vector c. The vector c will be 0, 1, 0, this one, minus 0, negative 1, 0. And that's 0, 2, 0. So voila. So that's the answer. We found c now. So c is this vector. So then if you want to write it, the final answer to the problem is the one we had before plus 0, 2, 0. Or if you want, you can write it as a single one like this, 10t minus cosine t plus 2 t squared over 2. Okay. One last item for today, definite intervals. So definite intervals, again, not surprisingly, they are done the exact same way. And let's put it on the screen right here. On the next page, you see how we're supposed to do it. What you do is you do the definite intervals of the x part, the y part, and the c part. And we have it right here. So to do the definite interval of a function, we do the definite interval of the f component, the definite interval of the g component, the second component, the y component, and the definite interval of the z component, the one that corresponds to k. Last example for the day. Let's do example 7. And you see it right there on the screen. It says evaluate this little definite interval. So we want to do the integral from 0 to pi of I plus 3 cosine t over 2j minus 4tk. Good. How do we do it? Well, one piece at a time. So this time I'm gonna keep the I, the j, and the k because I prefer the other one in case you didn't notice. I don't quite like I, j, and k. I'd rather have the components, but it's the same really. So I'm gonna do it. So what is the integral of just the I? Well, it's just t times I. So t I plus, then we integrate this part. What is the integral of cosine t over 2? So the 3 will stay there, and the integral of cosine is sine of t over 2. But then when I take the derivative of this, the derivative of t over 2 will have a 1/2. So to kill that 1/2, I need to multiply by 2. And that's the j part. And then for the k part, the integral of 4t, that's 2t squared, or 4t squared over 2. Okay. And we evaluate this from t equals 0 to t equals pi. So here we go, pi. So it will be pi minus 0 times I plus 6 sine pi over 2 minus 6 sine of 0 times j minus 2 pi squared minus 2 0 squared times k. And that's my answer. I just simplified a little bit. So this is pi I plus sine of pi over 2 is 1 and sine of 0 is 0. So this is 6j. And this is minus 2 pi squared k. And if you want it as a vector without the I, j, and k is pi 6 negative 2 pi squared. So either way is correct. Okay. So that's going to be the end for today. Are there any questions before we sign off? Okay. There doesn't seem to be any, which is good. Like I said, I mean, today's material for today, I consider it easy because it's essentially a review of everything we've seen so before. But now the only difference is that we have little pieces, right? So instead of having to do it on one function, we have to do it 3 times on the x, on the y, and on the z, on the I, the j, and the k. Other than that, it's pretty much the same thing we were doing before. Okay, so everyone have a good weekend. Stay safe, and I'll see you guys next week.